Welcome back, engineering enthusiasts, to another dynamic episode of Engineering Academy. Today, we're delving into the fundamental principle that underlies movement in our universe, momentum. From the intricate interplay of moving objects to its awe-inspiring applications in technology and beyond, let's explore the mysteries of momentum together on this thrilling journey. And remember, if you're moved by any of the revelations, just consider it a momentous event. Let's start with the basics. An object in motion is like that friend who's always either speeding up or slowing down. When a car speeds up, it gains momentum, just like how a speedy friend might get more energetic. Conversely, when a car slows down, it loses momentum, similar to a sluggish friend. This whole exchange of momentum is the fundamental principle behind motion, and you thought your friend's energy levels were unpredictable. So how does one object transfer momentum to another object? That's where collisions and interactions come into play. During a collision, momentum is transferred from one object to another. In an elastic collision, objects bounce off each other and momentum is conserved, meaning the total momentum before and after the collision remains the same. In an inelastic collision, objects stick together, and while the total momentum is still conserved, some kinetic energy is converted into other forms of energy, like heat and sound. Understanding these interactions is crucial in fields ranging from engineering to physics to sports science. An easy way to think about this is, imagine two pool balls on a billiard table. When one pool ball strikes the other, they both move in opposite directions. The momentum one ball gains is equal and opposite to the momentum the other pool ball loses. It's like a well-coordinated game where every strike is balanced and every collision results in an equal and opposite response. In the real world, momentum plays a crucial role in various phenomena, such as car crashes. When two cars collide, the momentum from each car is transferred, and analyzing this transfer helps engineers design safer vehicles. In the game Final Fantasy VII, the character known as Cloud Strife wields a weapon called the Buster Sword, which is a massive broadsword with incredible destructive power. Cloud's attack often involves swift, powerful slashes at enemies or charging up to execute devastating limit breaks. The visual effects accompanying these attacks typically depict shock waves or energy bursts emanating from Cloud's Buster Sword, illuminating the concept of momentum transfer. This portrayal showcases how momentum is incorporated into the game's combat mechanics, allowing players to harness the power of kinetic energy to defeat enemies and progress through the game. Now let's move over to the topic of impulse. Impulse is the measure of the change in momentum when a force is applied over a specific period of time. It's a fundamental concept in the realm of mechanics and plays a crucial role in various applications, from designing safety features in cars to understanding the mechanics of sports. Impulse is calculated as the product of force and the time over which it is applied. A large force applied over a short time can produce the same change in momentum as a smaller force applied over a longer time. An easy way to think about impulse is to imagine a hammer striking a nail. The hammer applies a large force over a very short period, driving the nail into the wood. This is a perfect example of impulse in action, where the hammer's force changes the momentum of the nail in a very short time. A real-world example of impulse is seen in airbags in cars. During a collision, airbags deploy to cushion the impact, reducing the force on passengers by increasing the time over which the collision occurs. This reduced force over a longer time decreases the change in momentum experienced by the passengers, thereby reducing injuries. In many video games, impulse plays a vital role in gameplay mechanics. For instance, in the game Rocket League, players use cars to hit a giant soccer ball, transferring momentum to the ball to score goals. The force and duration of contact between the car and the ball determine the ball's speed and direction, making impulse a key aspect of the game. Players must strategically control their car's speed and angle of impact to achieve the desired momentum transfer, showcasing the importance of impulse in gameplay. Let's move over to the topic of elastic collisions. Elastic collision is one where the total kinetic energy of the system is conserved before and after the collision. This concept is fundamental in the realm of mechanics and plays a crucial role in various applications, from understanding molecular interactions to analyzing macroscopic collisions. An easy way to think about elastic collisions is to imagine a pair of balls colliding in mid-air. When they collide, they bounce off each other and continue moving, but the total kinetic energy of both balls remains the same before and after the collision. This is a perfect example of an elastic collision in action, where kinetic energy is conserved even as the balls change direction and speed. A real-world example of elastic collisions can be seen in the behavior of gas molecules. When gas molecules collide with each other, they undergo elastic collisions, conserving kinetic energy and momentum. This conservation plays a critical role in the behavior of gases. Elastic collisions are integral to gameplay mechanics. For instance, in the game Angry Birds, the birds and obstacles often collide elastically. The kinetic energy is transferred from one object to another, making the collisions realistic and predictable. Players must strategically aim and use the bird's momentum to achieve the desired outcomes, showcasing the importance of elastic collisions in gameplay. The opposite of an elastic collision is an inelastic collision. In an inelastic collision, objects collide and stick together, and some kinetic energy is lost to other forms of energy, such as heat or sound. However, momentum is still conserved. In an inelastic collision, the total momentum before the collision is equal to the total momentum after the collision, even though some kinetic energy is lost. In an inelastic collision, sticking with our car crash example, the cars may crumple and stick together, absorbing energy and reducing the impact force of the occupants. This absorption of energy helps protect passengers, illustrating the practical importance of understanding inelastic collisions in designing safer vehicles. A common real-life example of inelastic collisions is catching a ball. When you catch a ball, your hands move backwards as they absorb the ball's energy, reducing the force transferred to your body. This energy absorption occurs because your hands deform slightly and move with the ball, converting kinetic energy into other forms of energy, such as heat and sound. This technique helps protect your hand by reducing the impact force and increasing the duration of the collision. In the game Minecraft, players can create elaborate mechanisms using pistons and other moving objects. When pistons push or pull blocks, they transfer momentum to those blocks, causing them to move. If two moving blocks collide, they may stick together or transfer momentum in a way that mimics real-world inelastic collisions. This gameplay mechanic allows players to explore the principles of momentum and energy transfer in a creative and interactive way. Force, on the other hand, is the driving factor that changes an object's momentum. In physics, force is defined as the interaction that changes the motion of an object. When a force is applied to an object, it causes the object to accelerate, changing its velocity and consequently its momentum. The relationship between force and momentum is described by Newton's second law, which states that the force applied to an object is equal to the rate of change of its momentum. For more information on forces, check out our dedicated video on this topic. To better understand this, let's use an analogy involving a shopping cart. Imagine you're pushing a shopping cart down a grocery aisle. The harder you push the force, The faster the cart moves, change in momentum. If you suddenly stop pushing, the cart slows down due to friction, illustrating how forces change an object's momentum over time. A common real-world example of force and momentum is seen in rocket launches. Rockets use powerful engines to generate thrust, a force that propels the rocket upwards. This force changes the rocket's momentum, allowing it to escape Earth's gravity and travel into space. The principles of force and momentum are crucial in designing and operating rockets, ensuring they can reach their intended destinations. In the game Kerbal Space Program, players build and launch rockets, applying principles of force and momentum to achieve successful missions. Players must carefully design their rockets and calculate the necessary thrust to overcome gravity and reach orbit. Managing fuel, engine power, and launch trajectories requires an understanding of how forces change the momentum of their spacecraft, making the game a practical application of these fundamental physics concepts. In linear momentum, objects move along a straight path, transferring momentum directly from one object to another. This is common in collisions where objects travel in straight lines before and after impact. Understanding linear momentum is crucial in fields like automotive safety, where engineers design crumple zones and other features to manage the transfer of momentum during collisions. In angular momentum, objects rotate around a central point, transferring momentum through rotational motion. This is common in systems like gears and wheels, where rotational forces and torques play a significant role. Understanding angular momentum is crucial in fields like robotics and mechanical engineering, where precise control of rotational motion is essential. Consider momentum as the flow of energy through a system. In this analogy, the system represents a path or conduit, while the energy represents momentum. Just as energy flows from one part of the system to another, momentum transfers from one object to another through collisions and interactions. The rate at which energy flows depends on factors like the force applied and the time over which it is applied, much like how the rate of momentum transfer depends on the force and interaction of time. In real-world collisions, some energy is always lost to heat, sound, or deformation. For example, when a baseball hits a bat, not all the kinetic energy is transferred to the ball. Some energy is lost as sound, the crack of the bat, heat, slight warming of the bat and ball, and deformation, temporary bending of the bat and compression of the ball. Similarly, in the video game Fortnite, when characters break structures with their pickaxe, the game mimics energy loss by including sound effects and visual cues like splintering wood or shattering bricks, representing energy dissipation. The behavior of colliding bodies also depends on their material properties, like hardness, elasticity, and shape. For instance, a marble and a rubber ball will behave differently upon impact with the ground. The marble, being hard and less elastic, will not deform much and will bounce higher, conserving more energy. The rubber ball, being more elastic, will deform more and might not bounce as high. In the video game Minecraft, different materials like sand, stone, and slime blocks exhibit different behaviors upon collision, such as varying bounce heights or breaking upon impact, reflecting their real-world properties. Many real collisions are complex and may involve rotational motion, friction, and other forces. For example, when a spinning top collides with another object, its rotational motion and friction with the surface affect the outcome of the collision. In the video game Elite Dangerous, when spaceships collide, the game takes into account not just the ship's speed, but also their angles, rotational motion, and the friction-like forces in space. These factors lead to complex and realistic interactions, as ships might spin, drift, or even break apart upon collision. The simulation of these collisions considers various dynamics making the gameplay more authentic and engaging. In conclusion, momentum is a fundamental concept that drives motion in our universe, from the smallest particles to the largest celestial bodies. By understanding the principles of momentum, we unlock the potential for innovation and advancement in countless fields, from transportation to sports to space exploration. Thank you for joining me today, and if you enjoyed this episode, don't forget to like, subscribe, and join our Patreon for bonus materials on all our subjects. Have a great week, and don't forget to never stop learning.